Hello and welcome to helpyourmath.com. In this video, we're going to look at even more examples of factoring. We're actually going to review all of the methods. So all of the methods that I came up with, if we have two terms, we look to factor by finding the GCF. We look to see if it's a difference of squares. Differences of squares are of the form first term squared minus second term squared, and that factors into root minus root times root plus root. A difference of cubes would be x cubed. The first term is a cube and the second term is a cube, and that factors into root minus root times first root squared plus the product of the two roots plus the second root squared. And it's very rare that this thing would be factorable. It's almost never ever is, especially if it's cubes and there's not a higher degree. Or the fourth thing it could be is a sum of cubes. The sum of cubes would be x cubed plus y cubed, and that would factor into root plus root times the first root squared minus the product of the two roots plus the second root squared. And again, very unlikely the trinomial will be factorable, but it doesn't hurt to do a quick check. Okay, what happens if we have three terms? Well, if we have three terms, always look first to see if there's a GCF besides 1. If the leading coefficient is 1, then we can do the target product target sum. So we might have something like x squared plus bx plus c. And if you can find that winning combination, so the winning combination would have a target product that multiplies to c and a target sum that multiplies to target sum that adds up to b. If you can find that winning combination, so let's call that winning combination d and e. So those are the two numbers that multiply to c. So we're going to say d times e equals c and d plus e equals b. And the leading coefficient is 1, so notice there's no a because it's 1. This would factor into the first term, well, the root of the first term plus d times the root of the first term plus e. So you can just plug those right in. It's a really nice shortcut. Is it a perfect square trinomial? Not a perfect trinomial, a perfect square trinomial. If it's a perfect square trinomial, how do we recognize it? Sometimes we don't, and that's okay. If the leading coefficient is 1 and you just kind of do the method for that, that's totally fine. If there's something kind of awkward, you might look to see if it's a perfect square trinomial, because those can have really big middle terms, and that can be less than pleasant to deal with. So if it's a perfect square trinomial, it comes in two flavors. We could have x squared plus 2xy plus y squared. So if you notice that the first term is a perfect square and the third term is a perfect square, look to see if the middle term is the product of the two roots doubled. And if it is, then it's going to factor into x plus y quantity squared. That was flavor 1. Flavor 2, we could have x squared minus 2xy plus y squared, and this would factor into root minus root quantity squared. Okay, what if the leading coefficient is not 1 and it's not a perfect square trinomial? That's when you want to use the target product target sum method to see if it is in fact factorable. So this is also sometimes referred to as the AC method. So for this, I say the target product is A times C, where A is the leading coefficient and C is the constant. And the target sum is the middle coefficient B. And so we look to find a combination of numbers that multiplies to the target product and adds up to the target sum. And we'll go through an example of that. Okay, what if there are 4 terms? Again, we want to look to see if there's a greatest common factor, or we want to see that if it's factorable by grouping. Okay, this has been a review. Let's look at a bunch of examples. In this first example, I see it's 3 terms, so it's a trinomial. I see we have a leading coefficient. It's not a perfect square, so I think we're going to have to use the target product target sum method or the AC method. And how does that work? Well, again, we're looking for a target product. We're looking for 2 numbers that are going to multiply to A times C. So we have 3 times negative 10, which is negative 30. The target sum is B, and let's see, what's in the middle? A 1. So what are 2 numbers that multiply to negative 30 and add up to 1? Well, that would be positive 6 and negative 5, right? Positive times negative gives me negative 30. 6 plus negative 5 adds up to positive 1. We can't use any shortcuts here, so we're going to have to expand the middle. When given the choice, because I have 1 positive and 1 negative, I like to put the negative first because then I don't have anything weird going on with that third term. So when I write this, I'm going to say 3w squared minus 5w plus 6w minus 10. So again, this is what we're going to do. We replace this middle term, the w, with these as coefficients. So it would be 6w and minus 5w because that adds up to 1w, right? We ensured that with that target sum. Now that we created 4 terms, we can factor by grouping. I grouped together the first 2 terms and the second 2 terms. And this is why I like not having a minus in the middle, because weird things happen when there's a minus in the middle. So that's why I put that negative term first. Now we're looking for the GCF of the 2 different groupings. So here we have 3w squared and 5w. The GCF there would be w. And then when I pull out a w, I'm going to be left with 3w minus 5. In the second grouping, I have 6w minus 10. They have a factor of 2 in common. I divide both by 2, I get 3w minus 5. And now what I've done, this is why factoring is so fun, we went from 3 terms at the beginning to 4 terms when we factored by grouping. Now we're down to 2 terms. Do the 2 terms have a greatest common factor? Yes, they do. This has a factor of 3w minus 5, and this has a factor of 3w minus 5. So I pull out that common factor of 3w minus 5, and then I multiply it to what remains. So I still have a w from the first term, and I have a plus 2 from the second term. And thus we have completely factored this delightful trinomial. Let's look at another one. Okay, so this one I see we have some fractions. Do you remember how to handle fractions? We want to clear out the fraction. We want to write the fraction as a coefficient, and that way everything else will be integers, which is going to be nice. So what we're looking for is a greatest common factor that's going to clear out those fractions. I see we have a denominator of 4, so we're going to use the 1/4. I also see that each term has an x, so we're actually going to factor out 1/4 x. What I like to do just to make it look a little bit nicer and easier to factor out the 1/4 is I'm going to rewrite it as 1/4 times what? So 1/4, this would be, well, times x cubed. Okay, that one wasn't so bad. Next we have 1/4, and I had 3 of them, so this would be 3x squared. And then, wait a minute, this last one doesn't have anything. So we're going to write it as 1/1. Now, I would like for it to have a denominator of 4 so that it looks like the rest. So I would multiply by 4/4, so I can just do that. And now I can say, okay, now I have fourths in the denominator. How many fourths do I have here? I have 4 fourths, so that gives me 4x. Now I can factor out that 1/4, and I also want to factor out the x, right? Let's not forget that they each have an x as well. So I'm going to factor out the GCF of 1/4 times x, leaving behind x squared minus 3x, because I took one of the x's away, minus 4, because I took one of that solo x away. Now we want to see if the trinomial is factorable. Inside the trinomial, the target product would be -4, and the target sum would be -3. 2 numbers that would multiply to -4 and add up to -3 would be -4 and +1. Looking at this trinomial, it does have a leading coefficient of 1, so I can just plug in -4 and +1 into the factors. Yay! So at the end, we're going to end up with 1/4 x times x minus 4 times x plus 1. And that would be a completely factored version of this beast over here. Okay, in our next example, what do we see here? I see 2 terms. Any GCF besides 1? No, 27 and 8 don't have any common factors besides 1. I notice that the variable is cubed, leading me to believe this might be a difference of cubes. Let's find out. Is the first term a perfect cube? Well, is 27 a perfect cube? It is. It has a cube root of 3, so this would be 3x would be the root cubed. And how about 8? Is 8 a perfect cube? Yes, its cube root is 2. So I know the root of the first is 3x. I know the root of the second is 2. And remember what cubes, differences of cubes factor into. So we have x cubed minus y cubed. We'll factor into x minus y. So that's going to be root minus root. 3x minus 2 is the first term factor. The second factor is x squared plus xy plus y squared. So x itself in this case is 3x. 3x squared would be what? Let's try it again. 3x squared would be 9x squared. Be really careful. Make sure you square the entire first term. So we're going to get 9x squared plus, we're going to multiply the 2 together. 3x times 2 is 6x. And then it's going to be the second term squared. 2 squared is 4. And just a quick check, we have a target product of 36, a target sum of 6. Going through the factors of 36, we have 1 and 36, no. 2 and 18 doesn't add up to 6. 3 and 12, no. 4 and 9, no. 6 and 6, no. So this would be it. This would be our final factored version of 27x cubed minus 8. How about in this example? This example, I see a trinomial. Greatest common factor is 1, so that's not helpful. Leading coefficient is 2, so it looks like no shortcuts. We have to use the target product, target sum method. The target product in this case, remember what that is? That's a times c. So that'd be positive 2 times negative 15, which is negative 30. The target sum, which is b, would be negative 1. Can we think of two numbers that multiply to negative 30 and negative 1? I think so. I think we did something very similar to this last time. It would be, in this case, negative 6 and positive 5, right? They multiply to negative 30, they add up to negative 1. I'm going to expand the middle, so I'm replacing minus x with these coefficients, negative 6x and 5x. So 2x squared minus 6x plus 5x minus 15. What I've done is I've created 4 terms, so now I'm ready to factor by grouping. Group our first term, 2 terms, group our second 2 terms. Now, in each of these groupings, look for a GCF. 2x squared and 6x have a common factor of 2x. That would leave behind x minus 3. In the second grouping, 5x and 15 have a common factor of 5, leaving behind x minus 3. I got this down to 2 terms. I have 1 term here and 1 term here, and those 2 terms have a common factor. They each have an x minus 3, and what's left behind from the first term, 2x. What's left behind from the second term, plus 5. So we would have x minus 3 times 2x plus 5 is what happens when we factor 2x squared minus x minus 15. A few more examples, you're doing great. What do we see here? I see 2 terms, GCF is 1. I see the cube, and I see a plus sign. So this leads me to believe we have a sum of cubes. Sum of cubes is going to be root plus root times root squared minus the product of the 2 roots plus the second root squared. So what is the cubed root of n? Well, that would be n. I'm sorry, what is the cubed root of n cubed? That would be n. What is the cubed root of 27? That is 3. So this would factor into root plus root is the first factor, and the second factor is going to be n squared minus n times 3 plus 3 squared, which would be 9. And this is not factorable. You can take my word for it. So this would be the final factored version of n cubed plus 27. In this example, we have 9x squared minus 100. How many terms do we see? 2 terms. GCF is 1. I see a square, and the only option for when we have a square is the difference of squares. That would be, I don't know why I put a parenthesis there. For a difference of squares, that's x squared minus y squared, and that factors into root minus root times root plus root. So let's see, is this a perfect square? Yes, 9's a perfect square. 100's a perfect square. The root of the first term is 3x, and the root of the second term is 10. So that's just rewriting these so I can see what the roots are. Now I'm ready to plug in. Root minus root would be 3x minus 10. Root plus root would be 3x plus 10, and that's as much as we can do for this example. Oh boy, this one's a beast. I don't like the looks of this one. Well, let's go through the checklist. It's a trinomial. GCF is 1 because 49 and 64 have no common factors. I don't really want to do target product, target sum. Nobody wants to sit here and multiply 49 times 64, so we better hope that this is a perfect square trinomial. Do we remember how to check that? Is the first term a perfect square? Yes, it is. This would be 7x, quantity squared. Is 64 a perfect square? Yes, it is. Its root is 8. Okay, so they're both perfect squares. Now comes the check with the middle. Is negative 112x the result of taking the 2 roots, 8 times 7x, and doubling it? So if we take that and then double it, do we end up with, well, in this case, negative, well, we'll just say 112 and we'll deal with the negative in a minute. Yes, we do. That does actually work. This is a perfect square trinomial. Woo! We don't have to use the target product, target sum. perfect square trinomial of this form, this is x squared minus 2xy plus y squared, is going to factor into root minus root quantity squared. So this will be root minus root quantity squared. I don't know why I put a square there. Let's try that again. Okay, so this is going to factor into root minus root quantity squared. Woo, that was way better than it could have been. And our last example, we have y squared plus 36. This has two terms. I don't see a common factor besides 1. It has a square, so we're not dealing with cubes of any sort. And it looks really nice, right? This is a perfect square, this is a perfect square. However, there's only a difference of squares. There's no such thing as a sum of squares in the real number system. So in this case, even though it looks really nice, it's not factorable. Or you can say already factored, so not factorable. And that would be it. These have been a lot of examples of using various methods to factor. Thank you for stopping by.